Alright, we are now recording. Okay, 30 seconds more. Okay, I'm going to stop. So if this was in Cartesian, let's say give the Cartesian equation with all this, we'd know how to do this. We'd know that this is our m, and this is x1, y1, and we would go y minus y1 equals mx minus x1, so it would be y minus negative 1 equals 2x minus 3. So and then we just simplify that and we have our equation in Cartesian coordinates. But when we are in parametric, now this is a little bit different than the type of problems you had on the homework for today. I just wanted to get you to look at it in a little different way. We need x in terms of t and y in terms of t. And every time t goes up by 1, see in this equation up here, every time x goes up by 1, y is going to go up by 2. It has to do with the relationship, fundamental relationship between these two things. Well, we still need that to happen. So if x had somehow t involved in it, when t goes up by 1, x is going to go up by 1. But we need y to go up by 2, like this. Okay? Now that's going to get the right ratio of how they're going to be increasing. And then we have to have them start out. Well, the x has got to start out at 3. When t is equal to 0, x will be 3. When t is equal to 0, y will be negative 1. And this will provide us with the right equation. So when t is 0, we're right on this point, and we move in such a way that every time x goes up by 1, y goes up by 2. And then if you solve this equation for t and substitute it in here, would lead you back to this equation over here. And give me a little feedback on number 2. You just write a sentence. Okay, and this class is so small with 6 people. I thank you, Rowan, for who's present here today, and I can tell, I can see we got all 6 people. So great. Yeah, I'm kind of taking it at a different angle than what you had to do with the way we looked at parametric equations last time, and kind of what the homework was taking you through. All right, let's go to the next one. give parametric equations that generate a circle of radius 2 centered at the origin. Okay, 30 seconds more. Okay, again, if this was give Cartesian equation, it would be x squared plus y squared equals 2 squared. But for parametric, x and y in terms of t, and you can do this in either order. Cosine here, and sine here, or sine up here and cosine here. It doesn't matter. It will change the starting point, and it will change the direction in which you rotate around the circle. This would give me a circle centered at the origin of radius 1. And then if we just plop 2 in front, that's now a radius 2. And by the way, if you substitute these into here, what would we get? We'd get 4 cosine squared t if you substituted this into here. 4 cosine squared t plus 4 sine squared t. And that, if you factor out the 4, this turns out to be 1, and it does turn out to be 4. It gives you, it comes back to the Cartesian equation of the circle. Okay, give me a little feedback on number 3. And again, that feedback portion is a real important part of this process of reflection on, I mean, you can kind of summarize it. If there's something that you got out of the activity, and you can kind of summarize it, that'll make it stick a little more if you can summarize it. Okay. State the derivatives of the 6 basic trig functions.
From memory?
From memory. Don't look any of these things up. Yes, very important. This practice quiz stuff is to exercise your brain. Call them retrieval practice. And what happens in your brain is if you don't use it, you lose it. That's how the neurons get wired. And so by reusing these things, you're reinforcing these connections, you'll remember it better in the future. But you subvert that whole process if you just look it up. And the other thing I want you to do is, if you just can't remember, what was the derivative of tangent? I can't. But if you force yourself to make a guess, you'll get a lot more out of the activities as well. again, you'll be able to, it's much more productive for your brain to have to adjust an answer and say, oh, geez, I had part of that right. I hadn't realized that. I remembered something. I just need to adjust this. You'll get so much more than if you just say, oh, I forgot, and don't put anything down. All right, 15 seconds more. All right, so I'm going to use a real shortcut notation. Prime. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is very similar to this. If the derivative of tangent is secant squared, you'd think the derivative of cotangent should be cosecant squared, but it also has a negative. Derivative of secant is secant tangent, and the derivative of cosecant is cosecant, just follows the same pattern, cotangent, but with a negative. All right, a little feedback on number 4. Okay, so a refresher on this seemed to be helpful, appropriate. All right, well, how do you define a vector? What is a vector?
Are you asking us, or you're?
Yeah, practice quiz
Oh.
question, so
Oh.
write it down. Okay, there's a lot of ways you could answer this question. And you could give it notationally, oh, this is what they look like, this is how we write them, and so on. But the essence of what a vector is that it contains two pieces of information. A direction and a magnitude. So for instance, the wind, we might say it's 50-mile-an-hour wind, or we might say the wind is out of the northeast. But if we give both the direction and the magnitude, then we have the essential information for a vector. Okay, and notation-wise, we'll get into that in a minute. Give me a little feedback on number 5. All right. Show multiple ways to write a vector, including the use of standard basis vectors. So let's say we're going to call it the vector A, and give me, a bunch of different A equals. Different ways you might write the vector A. And you can just make up any old vector. Thirty seconds more. Okay, so multiple ways. Suppose I had the vector 4, 1, which would look like this if it was in standard position. Standard position is putting its tail at the origin. All right. Now you could also state the vector by giving its magnitude, which in this case would be square root of 17. It's the square root of a squared plus b squared. And then you could also give its angle, the angle that it's tilted up at, theta. Theta is equal to the inverse tangent, because if you make this thing, make it a little bit bigger. So this is 4 and this is 1. The tangent is SOHCAHTOA opposite over adjacent. SOHCAHTOA opposite origin. The inverse tangent of 1/4. So there's two ways we can do this. We can also use the standard basis vectors I, which is a unit vector in the direction of the x-axis, plus 1j, which is the unit vector in the direction of the y-axis, like this. And are there other ways? Does anybody, especially those of you who've had it in physics and statics and stuff, are these basically all the ways that you give vectors? That's all that's coming to my mind. Alright, give me a little feedback on this, on ways to write a vector. A matrix. Okay. So we could do a vector in a sense is a matrix, but one of the dimensions is just 1. You could think of it as a 2x1 matrix. Alright, and then show multiple methods, including graphically, how to add these two vectors together. So, get the answer in as many different ways that you can. Okay, 30 seconds more. Okay, so the easiest way to add these two is you just add the x components, add the y components. And why does adding vectors work that easy? Because we can see it when we look at them graphically. 2, 1 is this vector. Now notice the horizontal component is 2. I'm not going to write the vertical component for a second. The next one is 3, 1. Now when we add them, we do this tip to tail method. So we're going to put 1, 2, 3. From here I'm going to go 3 over and 1 up. And the horizontal component here is 3. So we can see that if I make my final vector go from here to the original tip to the final tail, it's going to go over 2 units and 3 more units, 5 units. I'm going to arrive at this. And similarly, the up portions. 1 up, 1 more up, and you're going to wind up going 2 up here, like this. Alright. So that's one way that we add them graphically. There's another way that we add them graphically. And let me exaggerate the 2 vectors a little bit. 1 here, and suppose the second one was a little more different than that. It was like this. Alright. Then you make a parallelogram. This will work better. Let me make my vectors a little more different. Like this. You can do the parallelogram method for adding the 2 vectors, and then the sum of the vectors goes through the diagonal of this parallelogram. And this is the same as doing the tip to tail, because imagine moving this vector over to here, and then it's the tail of this more vertical vector placed on the tip of this vector, and adding them the other way. Alright, give me a little feedback on number 7. Should be shaking off some rust. Maybe it's been a while, unless you've had a bunch of science classes where you were using vectors, but otherwise it might be a while since you've done this. Alright. Find the magnitude of this vector. One, 2, 3, 4, 5 over and 2 up. It's right here. The magnitude is the length of the diagonal. And this is the Pythagorean theorem. We have 5 over and 2 up. So this is the square root. So this squared is equal to this squared plus this squared, or this is equal to the square root of the sum of the squares of these. So that's the magnitude of a vector. We kind of already had alluded to this, some of the other stuff. And then find a unit vector. So a unit vector has magnitude of 1 in the direction of 5i plus 2j. I'll give you a minute with that. 15 seconds more. Okay, so this vector was too big. It's not a unit vector, it's a little bit bigger than 5, because the square root of 25 would be a length of 5. Now, let's suppose for a minute that this vector's length was 2. Then, it's in the right direction, but if its length was 2, it's twice as long as it should be, so I just divide it by 2. If its length was 3, it's in the right direction, I would just divide its length by 3. In fact, in this, the unit vector in this direction, we'll call it u, is going to be 5I plus 2j divided by, well, it's about 5 times too long, or square root of 29 too long. You just divide it by its magnitude. So we could write this final result in a number of ways. 5 over square root of 9I plus 2 over square root of 29j. That would be fine to write it like that. Or you could factor out the 1 over square root of 29 out in front in parentheses, 5I plus 2j. And there we've got it. And so this is, if we'd have said, find a unit vector in the direction of a general vector A, the answer would be u is equal to A divided by the magnitude of A. That gives you a vector, so a unit vector has magnitude 1. Okay. And a little bit of feedback about 8 and 9. Okay, and Hisu asks, does parallelogram rule apply only when two vectors share the tails? Yes. We only use the parallelogram rule when we put them in standard form, which is tail at the origin. And then otherwise, we put tip to tail to add them. Okay, and some of you, this is new, about getting a unit vector, and some may have seen it before. Okay, when I teach like pre-calculus here, we usually go over it very quickly. Students only have like a couple problems on it. And that's it for the practice quiz. So, questions on homework. All right, if there were no questions on homework.
Can we do number 21, please?
Number 21, 12.1. So this is 12.1, number 21. And part A, eliminate the parameter to get an equation in x and y. Alright, so I really only have, I need to somehow put this into the one identity that I typically use, was somehow I need to come up with cosine squared t plus sine squared t equal 1. If I have the same angle here and here, then I know this is going to be true. Well, how do I get that from this? Well, I have to square the x and not square the y. And then I'll get that. And so then it will be 1. So, and then I'll just change this around, negative x squared plus 1. So now I see this is a downward facing parabola shifted up 1 unit. And then describe the curve and indicate the positive orientation. And then I'd have to plug in a couple points to see what orientation is. T goes, you know, it's going to start at, when I put t equals 0 in there, and then I'd have to, that would take me a little too much time. I think you can get that on your own. Does that answer your question? I think that was Matthew.
Yeah, I squared it, but then for some reason I thought we were supposed to somehow get it to like a circle or something, so I just got kind of confused, but that makes complete sense now.
Makes sense now. This is a problem. Now, what's crazy about these parametric equations is the things inside here give you deceptive information. I would think if x has cosines and y has sines, that we'd be getting some kind of circle in here. Not necessarily true. It's the relationship between the x and the y that matters. And so when we come up to here, there's no sine and cosine in this, and it's just a simple parabola. These things can be really, like for instance, if I had x equals t to the 4th, y equals t to the 8th. I'm thinking, oh, 4th power, 8th power. I'm thinking really, but what is this? This is y equals x squared. That's all it is. Because it's just a relationship between it. If you take whatever the x is and square it, power to power you multiply and you get that. So these, what the functions are in here can be really deceptive. It's the relationship between the x and the y. That's the big thing. So that's a very good problem to look at, and it brings out an important point. I'm glad you asked this, Matthew. Any other questions?
Hi, this is Rowan. I have a quick question just about parametric equations in general. So if you have a parametric equation, do both x and y need to be in terms of t? Or could you have like y in terms of x and then x in terms of t? Like I guess for our question in the beginning with like turning that line into a parametric equation, like what would stop you from just writing like x is equal to t and then y is equal to 2x minus 7? Like it's kind of like a cheaty parametric equation.
Alright, so let's come back up to here. You said in this one, you said y equals, you said x equals t.
Yeah.
And then y equals
Like 2x minus 7.
2x minus 7. Alright. Now, because that's what this will result down to. If you solve this from y. Alright, now notice what you did. You don't need this one. This is the Cartesian equation. So this is not parameterized. If you parameterize, then yes, both x and y have to be in terms of that parameterized t in this case. Okay? This is just a Cartesian equation, and you throw away this one.
Okay, thank you. Yeah, good to know.
Okay. When you come up with something that's very different like this, it's those kind of questions, I think, that really add the insight that you come up with. Well, what about this? What about this? that really develops your depth of understanding of it. So great job, Rowan, of just trying to look at it in a different way and ask all kind of questions that you can.
I have a question.
Yeah.
So in terms of t, is that kind of like the tangent point of the line?
Back to the same problem?
For any kind of parametric equation, because t equals whatever it is, and you get the coordinates for x and y.
I'm not sure what you mean by the tangent point of the line.
Like at t equals 1 hour, you went 3 miles up, and then, but your speed was like only 2 miles an hour. Like I'm trying to visualize what t does for us in terms of real world problems.
Okay. Yes, suppose, let me give a couple. If I take t equal to 0 here, we're going to wind up with 3 for the x and negative 1 for the y. And if t is equal to 1, we're going to come up with 4 for the x, and we're going to come up with 2 minus 1, which is 1 for the y. Alright, now this equation over here resolved down to 2x minus 7. And if I'd have just plugged in 3 for the x here, I'd have come up with negative 1 for the y. If I'd have plugged in 4 for the x over here, I'd have come out with 1 for the y. This parameterizes it though, and what we're going to see when we get into 3 space, how important this is. We're not going to be able to do what we'll call them space curves, like lines, or it doesn't have to be straight lines. It can be, kind of circles in space or spirals and all kinds of strange shapes. But we'll think of it as a miniature flying saucer that's zipping around in 3-dimensional space and then creating a trail. And then that trail that it creates is, the curve that we wind up having. And we will wind up, even when it's not the case, it'll be very insightful to us at times to think of t as time. And then we can actually look at things like speed. How fast was it going? Well, just like you were saying, Kylie, like this could be 1 hour. In that 1 hour, we move from this point 3, negative 1. Now we can kind of, graph this thing a little bit. From 3, negative 1 to the point 4, 1. And so we traveled in a straight line from here to here, and it took 1 hour, and it looks like we moved a little more than 2 units, and we're going a little faster than 2 units per hour, and all this kind of stuff, and we'll wind up taking that kind of perspective, and that's probably about as simple a perspective as we can with the parametric equations, is having t be the time, and then, yes.
May I try a quicker approach to address Kylie's question?
You bet.
The purpose of parameterization is that it enables us to ignore the vertical line rule governing functions in 2D space. That's what allows us to draw a whole circle using parametric equations instead of drawing 2 half circles using Cartesian equations.
That's a really nice feature of parametric equations. It does require that we have 2 equations instead of 1, but then we can get the entire curve. And in 3 space, when we go there, it'll make things possible that just really wouldn't be possible at all.
Is it kind of like magnitude?
Magnitude in what sense?
That it's giving you like, I'm sorry, vectors. That's what I meant. That it's giving you direction and the magnitude, but in terms of time.
We're eventually going to be getting to that, where we're going to take what's called vector functions, and we're going to be having objects moving in time, but we'll imagine all the vectors in standard position, and then the little tiny spaceship is only at the tip of the vector, and the tip of the vector will be moving around in space, and it'll be mapping out a space curve for us. Yes.
I just have one more question. I know we didn't get to it last lesson, but you were going to explain how the Cartesian equation and the parametric equations intertwine and kind of equal each other out.
And that was like the last problem.
Yeah, they look very similar when you took the derivatives of both,
Yes.
but one of them was about double.
Okay, so let's go back to here. So we're looking at the derivative dy dx, and when we did we said that's dy dt over dx dt, and then that reduced to 7 over 6t right here. Now, when we do it all again, but first convert to Cartesian equations, when we converted to Cartesian, we solve for t, and the y equals 7t plus 5. That was the easier one. We got this equation. We substitute this in for t into the more complicated equation. And then we took the derivative of both sides, and with d dx, kind of using implicit differentiation, and we get this one over here, 49 over 6 times y minus 5. Now, this answer doesn't look like this answer. But they mean the same thing. This one is in terms of the letter y, while this one is in terms of t. How can I show that they really mean the same thing? Well, let's continue out with this. This is 49 over 6. Replace the y with 7t plus 5. Y is 7t plus 5. So this y got replaced with 7t plus 5. Now, these 5's kill each other off, and we got equals 49 over 6 times 7t. Now, we think it's going to read it all down to 7 over 6t.
We have to square.
It will.
Oh no.
Reduce this, divide this by 7, divide this by 7, and then we get 7 over 6t. So we see that it's the same answer, but just in different formats. And if you were parametrizing and you wanted your derivative in terms of t, you can get it that way. If many times you're not able to get rid of the parameterization, if it's really complicated situations. sometimes you can't, and that's the best you can do. But if you were able to get rid of the t, you'd get the equivalent answer over here. So thanks, Kylie, for reminding me to come back to that, finishing that up.
Thank you. That clarifies it a lot.
Good. All right. Any other questions? Very good questions. Gosh.
I do. It does tie into the question that you just answered, but it has to do. It does have. Okay, 69 and 70, and it's to do with the process and less the question itself.
Okay.
So, with 69, I was able to come up with the right equation for the derivative of dy dx by going through the whole dx dt dy dt dance to end up at -8 cotangent x, and that was to establish the tangent line of the ellipse at t equals pi over 2, which puts it at 0x and 8 sine, and 8 on the Cartesian graph, which means tangent line 0 if we plug the x coordinate of that 0 into -8 cotangent x. But what I do not get is I couldn't figure out a way to eliminate the parameter for 69, and I didn't worry about that. But for 70, I tried to eliminate the parameter and then take the derivative of that. And also the other approach of doing dx dt, dy dt, and putting dy over dx that way. And I wound up with two different results, with two different derivatives.
Okay, let me address your first question, which is how to eliminate the t in something like this. And the answer to that, there's a trick involved. When there's sines and cosines, you're always going to use this. The trick is, how do you get to this from this? Well, this one is simply x squared. This one is y over 8 squared. And voila, we have the Cartesian equation.
Okay.
All right. And then you had a second question? I wasn't sure about that.
I was wondering why I got two different results for taking the derivative of both parametric equations directly, as opposed to eliminating the parameter and then taking the derivative of that.
Okay.
And it is related to the question that Kylie Jackson just proposed earlier.
So you got two different answers, one in terms of t and the other not involving t, right?
Yes, and to the best of my knowledge, I got rid of dt by doing the whole Leibniz derivatives are fractions dance, and I got a result for dy dx, which is not the same. Which was not the same result that I got from just getting the derivative from eliminating.
It sounds like you were doing the same kind of thing that I was doing on that last problem for Kylie, but you weren't able to get them to match up.
Yes.
Okay, so let's hold on to that problem, and today, as time permits, if we have time to come back to that, I'll probably have to, do number 70 all the way out, and then we could look at that.
Okay.
And all right, where we are right now is just about at break time. So we're going to go into 13.1, vectors in the plane, and but let's take our break first, and so we will start again. "15 minutes from now, 6:43 p.m. And the topic, vectors in the plane, is in contrast to the next section, which is going to be vectors in 3 space. So 13.2 is kind of where we're heading, and we're going to be working in 3 space throughout Calculus 3, and that's really the focus of Calculus 3, is how do you do calculus? Because our real world has 3 dimensions. How do you do calculus in 3 space? And one of the keys is vectors. But 13.1 is just a review of vectors in ordinary 2-dimensional space with just x and y. But we're going to pay special attention to subtraction of vectors because it's something that happens so often, and we want some big shortcuts for how to very efficiently subtract vectors. You can very efficiently add vectors with the tip-to-tail method. Well, what about subtraction of vectors? We'll look into that when we come back from the break. And before I take my break, does anybody need to talk to me individually? All right, let me mute, and I'll see you in a little bit. All right, well, we'll get back to it. So, vectors in the plane. Subtraction of vectors. And we will do so much subtraction of vectors in Calculus 3 that an intuitive understanding of this topic will be very useful. All right. Find the vector from 3, 5 to 7, 6. Now, if you have some graph paper, or if you print out some graph paper, it might be helpful. I'll be doing it on this grid on the screen. Okay. But go ahead and do this on your own and draw it. Then write down the resulting vector if the direction is reversed. So number 1, go ahead. And then and after, all right, we'll just go one at a time. Just do number 1, find the vector, draw it. I'll give you just about a minute to get ahead of me, and then I'm going to do it. Okay, so the vector from the point 3, 5. See, now if I was doing the point 3, 5 and I did this, I said, oh, here's 3, 5. The vector from the point 3, 5. That wouldn't be right because it didn't say 3, 5 as a vector. It said 3, 5 as a point. So I want to take that away. And I just want the point 3, 5. All right, now there's a hard time, this gives me a hard time when I try to make points, so let me put a little x. From 3, 5 to 7, 6. 7, 6. Okay, so to find the vector from there to there and draw it, looks like this. Then write down the resulting vector. All right, so first of all, I haven't really totally found that vector. I need to state what that vector is. That vector looks like it's going 1, 2, 3, 4 units to the right and 1 up. Then write down the resulting vector if the direction is reversed. If I reversed it, all it would mean is I'd be going in this direction. And if I was reversing it, I'd go from here, left 4, and down 1. So when you negate each coordinate, it reverses. Okay. Now, number 2. Find the vector from 3, 2 to 5, 4, draw it. And then also, of course, you got to write down what the vector is, like we did. And then find the vector from 3, 5 to 7, 6. So I'm going to give you a minute for 2 and 3. Some of these, selected ones of these, I'm going to have you work in your groups, but not right now. Right, from 3, 2 to 5, 4 find the vector from there to there, draw it. And what is that vector? That vector is, well, it went to the right 2, and it went up 2. And then number 3, find the vector from 3, 5 to 7, 6. Now, that's the same problem that we just did over here. But notice, it says from, these are in vector form, while these were in point form. The point form ones make intuitive sense. To go from this x coordinate to this, from this x point to this x point. Let's do it. But when you see them from this, there's a lot of assumptions that have been made. And this is the kind of notation we're going to run into at times. What this is going to assume, I want you to get used to these assumptions. It assumes that both vectors are in standard position. Now, both vectors in standard position means standard position is tail at origin. And this is going from the tip. It's kind of like the tip of that to the tip of that. And so it's kind of assumed that we're going from. So we'll wind up seeing, find the vector from this vector to this vector. It'll assume they're in standard position and you're just going from one tip to the other. It'll be the same answer.
The question. I got confused with the number 1 from the 3 and 5 to 7 and 6.
Yes.
And okay, this is not a vector, this is a coordinate. So you pointed at the 2 coordinates here, and you subtract from the 3 to 7, x1 minus x2. So you got -4. Y2, y1 minus y2 is you got -1. Then after we do that, how do we know which direction this resulting vector is heading? Because this one is going to left side, but this one you said the 3 to 5, 4. Then if I do the same way, 3 minus 5 is -2. So this gotta be -2, and this one is also -2. That means this arrow has to go the opposite side.
All right. You are bringing up a great point. So we'll go right to that point since you're bringing it up for us. So let me create a little space here. All right. Suppose you drive from mile marker 3 to mile marker 8. And here's home. And the mile markers grow as you move. Let me so you go from mile marker 3, 8. Now, you drive from mile marker 3 to mile marker 8. We say that you change is do we say that our change is in the positive direction or in the negative direction? Our change is clearly in the positive direction because 3 went up to 8. So the change is, now we always go from, if you want to get the sign of this correct, you have to put from the destination minus the start position. It has to be in that order. 8 minus 3 to get the sign correct on this. If you take the start position minus your destination, you'll get it with the wrong sign. You'll get negative 5 over there. Is that making sense?
Yeah.
Now, how that applies to here is so you're seeing, and that's kind of what we were going to be getting at as this goes in, is when you go from this point to this point, if you take it in this direction and say, the vector is going to be 3 minus 7, and then 5 minus 6, you're going to get this one, which is not the vector from this to this. That's the one that if the direction was reversed, you would get this. So instead of doing this, you have to do, for the subtraction of these things to work out to be the vector that is correct, you always have to say where you end up with minus where you started with. So you've got to do it in this order. 7 minus 3, 6 minus 5, 4, 1. All right. Any other questions? Okay, and then, all right. Let me have you do number 4 and number 5.
Hey, can I just skip number 3?
Did we skip number 3?
Kind of.
Oh, okay. I didn't write down the answer, but it's the same answer as before. The answer is 7 minus 3, 4, 6 minus 5, 1. Okay. And the main thing I wanted to point out, it's the same question as this one, but it has all these assumptions involved.
Okay.
All right. So go ahead and get your answers for 4 and 5. And go ahead and mute your mics now too. We got somebody that doesn't have their mic muted. We're getting some extra noise here. I think it's fixed now. All right, let me go over the answers real quick here. So take your, find the vectors from the tip of that to the tip of this. We just take the destination minus the x position of the destination minus the x position of the original. Oops, 6 minus 5. 4, 1, like this. And from the tip of 7, 6 to the tip of 3, 5, this is the start. This is destination. And then we're going to go the vector from the tip of there to the tip of there is, hang on just a second. Hey, thank you. This is 3 minus 7, so it's negative 4, and 5 minus 6, so it's negative 1. When we turn it around, we're going to get this. So we can draw this and see this relationship. All right, any questions? Okay, now, when you go to number 16, go ahead and write a description of these two things. And this one, I'm going to have you type it up, enter it into your group chat. Your answers for A and B. Don't hit enter yet, but just type it up. And then when I give you the cue, go ahead and hit enter. Go ahead and hit enter. All right, group 1, how would you describe A?
Let's see, my group said we could have the destination minus the start point. And then another suggestion is that you could have like W plus R, but instead of R, it's like the reverse of R. So W plus the reverse of R.
W plus the negative. Negate each of the coordinates of R, and so on. Okay?
Yeah.
All right, that's a good start. If I was to describe W minus R is a vector from the tip of something to the tip of something else, what would it be? What goes in the first slot?
I would say R.
From R to the tip of, and you put W over here?
Yeah.
And how does this relate to what we were talking about over here, from the destination to the from the start point to the destination? So Can anybody explain why this has to go from R to W and not vice versa because of this?
Is it like something like the absolute value?
Okay. It kind of really, when you take the absolute value, then it doesn't matter which order you take them in, because the absolute value would just kind of make it always the same thing in either order. Okay. And when we do subtraction of two vectors will always take us from the So we were looking back here, two vectors, find the tip of that to the tip of that. We had to always start with the destination minus the start position. The subtraction of two vectors, when we visualize it, will always take the first vector as our destination. We'll always look at the second vector as our start position. Now, why do we do destination minus the start position? Because
We want to know the vector's change
yes,
in
the
position.
change is always what you ended up with minus, and if a price of something went from, you know, $1 from $10 to $12, we'd say the change was positive 2. We always take the final position minus the start to find the change. Always do that. And so destination, start, so R is the start position, so it makes sense now. Vector from the start to the destination when we describe it. So we got to reverse these two when we're doing this. And so the second one is R minus W. This one is just the opposite. It goes from W. The start position is always the second case. To the destination. Right here.
Oh, the question. So I have a little difficult time to understand the vectors W and R are in standard position. Standard position means it's start from origin, isn't it?
Correct.
Yeah. Then how do we know what W means and which one is R means? It's just too vague.
All right.
Yeah, so that's why if we says a vector 3 and 7 or 4 and 6, you can find the vector on the plane, and you can see which direction it is going and find whether it's a subtraction or addition of vectors. But in this case, I have difficult time to figure out which one is a destination and why that is a destination and R is a starting point position. I don't know how it became the start position either.
Okay. Why it becomes a starting position is just because of its position in, if we have W minus R, whichever one is first is the destination, and whichever one is second is the start position, because that's how change is always defined. Change is destination minus the start. And that's, so if we're going to look at a subtraction and give it meaning, even if it's vectors, we'll look at a subtraction of vectors as this is the amount of change. W minus R is the change. And it only has that interpretation if that one was the destination and that one was the start. So if I had an R here, W here. Then if I had this, we can think of this as the amount of change, the difference between the two vectors. But how do I look at this? It's really confusing. Some people will put it R minus W. Somebody else will put it W minus R. But if we get used to this, it's when we label this, we have to label it as destination minus the start. And which vector did we end up at? W. Which one did we start out at? R. So this is W minus R, not vice versa. Okay, let's go on to number 7. It would be easier to remember if W minus R went from the tip of W to the tip of R in the order that they are written. Why is the order reversed? We will explore this with the following questions. So we kind of did this out of order just because we had some questions. The context of this question is no longer vectors, just numbers on a number line. If you start at 8 on the number line and end up at 2, what is your displacement? And let's look at that. If you start at 8, end up at 2, this is displacement is another way is how did you change? Did you go in the positive direction? No. Your displacement was -6. So the connecting concept is your displacement or your change is your final position. We ended up at 2 minus our initial position. We started at 8. Okay. So it's just reinforcing the same basic concept. You start 5 miles from home. You drive in a straight line directly away from home till you're 20 miles from home. What's your displacement? It's got to be, well, it makes sense that your displacement was positive 15 because you're going to take your destination minus the start position. And so, or final position minus initial position. So it's 20 minus 5, which is 15. All right, so I want you to do D and E on your own. Let me give you some time for both of those. Okay, go ahead and when you're done, enter your answers into your group chat. Give you a minute. Okay, so group 2, what do you have for D?
We said that it was like with the brackets 4 comma -2.
And how did you get that?
Oh, so I know like what we talked about earlier, like if you're going from 1, 4 to 5, 2, you can just flip them and like subtract them. And so 5 minus 1 is 4 and 2 minus 4 is -2.
Great. All right. And let me just show you one other thing. If you were going from 1 to 5, how would you do that? You'd add 4. If you were going from 4 to 2, how would you do that? You would subtract 2. So what kind of process would take you from one to the other would also give you this stuff. Okay? And what do you have for part E?
We have from go, we think the vector we're looking at is from point P to point.
Vector from the tip of P to the tip of Q, because that's destination minus, or final position minus start position. Okay. Let's go to number 8. A different way to view subtraction. Some other ways to interpret 8 minus 5. Number 1, how much larger 8 is than 5? Number 2, if 8 is my final position and 5 is my initial position, then 8 minus 5 is my displacement or my change. Number 3, 8 minus 5 is a number you need to add to 5 to get to 8. So that 5 plus 8 minus 5 gets you to 8. Now, we'll focus on this third interpretation. So, this third one, we have, if we think of this as vector A, this as vector B, and let me shrink this so you can see it. Draw B minus A on the graph above. Come on. All right, let me give you a moment. So it has to be, this is my final position. This is my initial position. So I'm starting at A and going to B. So this is B minus A. Now it says you can think of B as the final position, A is the initial position. And thus B minus A goes from the tip of A to the tip of B. That's how we were thinking about it. Sometimes it is easier geometrically to think of B minus A as the vector you need to add to A to get to B. So just like we were thinking with 8 and 5, this is because A plus B minus A is equal to B. What is the vector I need to add to this one? And we do the tip to tail approach to get to that one. All right. So do the following B minus A problems by asking, what number do I need to add to the x component of A to get to the x component of B? And then do the same for the y components. So it's You're going to get the same answer that you'd get before, but it's just thinking of it slightly different. So let me give you 30 seconds to get your answers for 1 and 2. So, this first one, I think, so this is my B, this is my A. What do I need to add to the A to get to the B? So I could do this component by component. 8 minus 2 and just get 6. 3 minus 1 and get 2. I could just get it that way, but we're thinking about it in a different way here. What do I have to add to 2 to get to 8? 6.
I have to add difference of 8 to 2 in order to get 8.
Say that again, you're a little choppy.
What I have to do is add the difference of 8 and 2 to 2 in order to get 8.
8, that's right.
Isn't that the algebraic way of thinking about this?
Yeah, this could be a simple algebra. What do I have to add to 1 to get to 3? It would be this. So it's just a different way of looking at it. And this one. What would I have to add to 5 to get to 7? 2. What would I have to add 11 to get to 12? 1. It's just like 8 minus 5. So be thinking of, what do I have to add to 5 to get to 8? That. All right. And note, the problem 8, 3, vector 8, 3, minus the vector 2, 1. It's actually much easier to do by just subtracting the x components, subtracting the y components. But geometrically, the similar problem below is easier by drawing the vector you need to add to A to get to B. So draw B minus A, and what's missing is the picture. Let me draw the picture that was supposed to be here. And we'll have A, B here. And B, B here. So go ahead and draw B minus A. Let me give you a moment here. Alright, so this vector B minus A, we always are final position minus initial position. We start at the tip of A. Now we also are going to look at it now. B minus A, we'll look at it. What do I need to add to A to get to B? I need to add this vector right up here. Alright, that takes us through all the topics that we needed to get through on this basic review of two-dimensional working with vectors. And are there any questions?
I have a. Oh.
Yes.
So my question is that, like, I guess in some of the other math classes I've taken, when we're subtracting vectors, like we just did it a different way. But maybe what I'm thinking is that like what we're doing now is basically we're only dealing with points here because we're looking at the tips of the vectors. So like there's really no reason to say that they're vectors at all because they're just points. So like if we were to include the entire vector in some sort of arithmetic, like, you know, subtract the entire vector b from the vector a, then do you just like do it the same way that we added the vectors by just adding the components? Then you just subtract the components? Or like, yeah.
Okay. This is Rowan, right?
Yeah, this is Rowan.
Okay. So there is no other way. It might feel like we're doing it different because we're only looking at the tips in standard position. But when you, well, actually, I guess you can visualize it in many different ways. But the visualization that we're going to use most often is for, you know, two vectors being subtracted, r minus w, is we're going to visualize them in standard position. R, w in standard position. And then, now, one of the other ways you might have learned before might have been do this. So negative w is just the same vector but putting the arrow down here. And then you move this one tip to tail over here. So this should be parallel to that one. Same distance, kind of like this. And then maybe I went a little bit too far. Go to about here maybe. And then, so if that's the case, then we take r plus negative w together, and then we get this. But this is also the same thing that we'd be getting, this green arrow, as if we said, this is my destination, this is where I start, so I start at w, and I go to there. Only works if this is in standard position. I'm getting the same vector. If I'd have drawn it proportionally, this one looks a little smaller than this one. But if I'd have drawn it a little bit better, we'd see that they're coming up to be exactly the same thing. Am I kind of getting at your question there, Ron?
Yeah, that answers it perfectly. I was just like, for some reason I just wasn't able to see that they were the same, but yeah, your drawing shows it pretty well. So thank you.
Okay, I think that's a good point that you're making too, is connecting back to maybe some other ways that you might have added or subtracted vectors in the past.
So this is the simply saying that as the book describes this triangle, the method, the rules, to think of the way of find the difference between vectors.
Yes, and there are so many different ways that we could do this. And if you got confused today, and you say, oh, I don't like this way of doing it, you'll probably be okay too. But if you can get some added insight into subtracting a vector so you can do it really quick and intuitively, it'll be worth the effort. If you go back over things and just be able to get the subtraction of vectors from standard position of them, Although this is the way that I would have taught this if this was your first introduction into vectors. It's not very efficient, and it's much quicker to look at it as, you know, what do I add to one vector to get to the other, or, you know, go from the tip of the initial vector to the tip of the destination vector. Okay, anything else? Any other questions?
Okay, yes, I do. With this most recent example here, you've shown that the value of the vector is the same. The green line is the same in either case, whether we are simply subtracting vector w from vector r, or when we're adding a negative vector w to vector r. But in this example that you've just shown, while the magnitude of the resultant vector is the same, you've shown me two different positions, which makes me ask, is adding a negative vector w the same as subtracting a vector w from vector r?
We say that these vectors
Are the same magnitude.
yes, they're all the same magnitude, and if I kept them exactly the same direction, then we call them identical vectors. It's more like the wind.
Okay.
Like other, these are all exactly the same vector. And you
Okay.
can move the vector wherever you want. We have only one preferred position, and that is standard position when you put its tail at the origin. But other than that, they're all identical, and they don't have to be in standard position. We just like them to be in standard position when we work with it, like when we add them and subtract them and stuff.
Okay.
Okay, and that's
Fair.
a good point. I'm glad you're bringing that up to really emphasize that. That vectors are kind of like, current in a river, or wind, or electrical current, and so on. And we can move them all around as long as we keep the direction and the magnitude the same. It's exactly the same vector.
Okay. Fair enough. Were we going to run through 70 very quick?
Yes, that's what I was going to do. Just make sure that there's no more questions on this, though.
Okay.
Everybody good with this? 13.1? All right, well, let's look at number 70. And if you didn't have any questions on 70, this part is optional. You could check out at this point. But if you do, let's look at this. This is number 70 and 13.1.
And my question was taking the derivatives of the parametrics separately and then doing Leibniz notation versus eliminating the parameter and then taking the derivative.
Right. We'll get it both ways, and we'll see. That should be the same answer either way we do it. All right, so A determine dy dx, and then we're going to find dx dt is 2, dy dt is 3t squared. So dy dx, two different ways we can do it. One way is this way, dy dt over dx dt, 3t squared over 2, 3 halves t squared. The other way is we could
Do the derivative sep.
we could do the Cartesian
Yeah.
equation.
Eliminate the parameter.
And then, so let's solve this first equation for t. T is 1/2 x. Now substitute that into the other equation. Y equals 1/2 x cubed. So this is the same as y equals 1/8 x cubed. And then if I did dy dx, I'm going to get 3/8 x squared. Now, let's go back and put the x in. But the x was 2t.
Oh, that's the step I was missing. Okay.
Okay, so then dy dx is 3/8 times 2t squared, which is 3/8 times 4t squared,
4 cancels left.
which is 3/2 t squared, same answer that I was getting before. So it
Okay.
checks either way. I'll get the same answer.
Okay.
Okay,
Thank you.
you're very welcome. And is there anything else? All right, if nothing else,
Thank you, Mr. Shankin.
you're very welcome. And I'll stop the recording.
Again, thank you.